So to prove this, what we do is consider we're going to be considering the contour integral of this. So f of z will have poles at zj, but cot pi z will also have poles. So cos is 1 over tanh, and 1 over tan. Tan is 0 at multiples of pi, n pi. So cot has simple poles at n pi. So cot pi z will have simple poles at all of the integers. So what we do is we consider the following contour. It's an infinite contour. What I'm going to try and draw is, so I'm drawing all of the poles of cot pi z. So they're at 1, 2, minus 1, minus 2, and so on. And then this goes on forever. The important thing is, this is x, this is y, just along the x-axis. Dot, dot, dot. Now, for my choice of contour, what I'm going to do is choose a square. So this is meant to be a square of size. This is going to be n, and this is going to be minus n. So the size of my contour will be n plus a half, and along here it's going to be n minus a half. So this point here would be n plus a half and n plus a half times I. Okay, so it's a square where the sides are length 2 times n plus a half. Okay, so that's my contour. So, I mean, the reason for putting it halfway between, it doesn't particularly matter whether it's halfway between 2 or a third of the way. It just needs, we don't want the complication of having to deal with this going through a pole. So we just choose to make the contour, whatever happens, not go through these poles at the integers. So what we want to do next is then show that this contour integral, the integral itself, as n goes to infinity, so n is an integer which is going to infinity, we want to show that that quantity actually is 0. So I'm going to write this as gamma sub n. So to show that this is 0, we're going to need to consider how big this quantity here is as z gets large. So the modulus of cot pi z is from a much earlier result we derived, where it's the modulus of, obviously, cos pi z over sine pi z. And a long time ago we actually derived that the modulus squared of cos z is actually cos squared plus sine squared. So it's actually the modulus of cos pi z ends up being cos squared pi x plus sine squared pi y. And a long time ago we derived that the modulus squared of sine z is sine squared x plus sine squared y. So if we replace z by pi z, we end up with sine squared pi x plus sine squared pi y. Okay. Then I need to take the square root. So what we notice is that as y gets very large, we can forget about x. Well, obviously this only gets as large as 1. So as y gets large, this tends to 1. So along here, this thing here is going to be modulus 1. Along here, where y is also large, it's going to be modulus 1. Along here, where y varies from being something not so large to something large, this will end up being something less than 1. Basically, we've got x is a half. Well, sine squared is going to be 1 here along here, so this will always end up being modulus less than 1, and the same here. Okay, so whatever happens, this is going to end up being modulus less than 1, less than or equal to 1. So that means that because we have this condition here, z times f of z will tend to 0, this integral will tend to 0 along all of these 4 sides of the square. So we therefore have that this is equal to 0. Now this 0, this has also got to be equal to the sum of all the residues. So what residues do we have inside here? Well, we've got the residues from the fz cot pi z. And these are made up of 2 parts. There's the residues, which are just simply these poles of cot pi z without the interference of fz. But also you've got the poles of fz, some of which might just overlap with one of these. So this is why we've got that n is not allowed to be any of the poles of f of z. So for example, if we had f of n was 1 over n squared, for example. Now, if it's 1 over n squared, then we've got a pole at n equals 0. So we would not include the term n equals 0 in this sum, which sort of makes sense, because if we did include it in the sum, then we would get an infinite value. So this is simply saying we don't want any infinite values of f in the sum. So first we work out what the residue of this is at z equals n, and where n is not equal to any of the poles of f of z. If it were equal to one of the poles of f of z, then it would not be a simple pole anymore. Okay, so this is guaranteed to be a simple pole. So we can use the p over q thing again. So we've got cos over sine, differentiate the sine. So we'll end up with f of n, substituting in, cos pi n divided by sine pi n. And we differentiate that, so that will give us pi times cos pi n. So now you sort of see where all this is coming from. So this simply then gives us f over n, f of n divided by pi as the residue. So so the sum of all of these is going to be the sum of f of n over pi over all integers except any integers which match the poles of f of z. And those are the residues that we have left. So basically, so we're going to have, first we sum over all of the integers which are don't coincide with poles of f of z. And we've just said that's going to give us this. So we're not multiplied by 2 pi I because it's equal to 0. So, and this is n is not equal to zj. And then we're left with the sum of the residues of any of the poles of f of z. So if we simply move this onto this side and multiply by pi, we end up with this formula.